So, welcome to the final section of medium access. So, the final section covers CDMA. And, well, CDMA, if you look at it the first time, it's a bit of strange, at least for computer scientists. You see, okay, we send at the same time, same frequency, so that was something special. We do not have to plan frequencies like, in the other cellular networks. If we use FDM and TDM, we have to avoid overlapping in time and or frequency. So now we use something like a code. I gave you the example of the party with the different languages. And I also explained the idea of having orthogonal codes. So this slide where I showed you the CDMA in theory is basically the key slide for it when I gave you a very simple example. Once again, this is very simplified. Why simplified? Not to confuse you, but in real life, you will not have these nice superimposed signals where you have more or less all the symbols in phase kind of synchronized. You will have a lot of noise, interference, and many more problems. So please try to redo this simple example, just that you understand the basic idea. And I also showed you that the keys AK and BK, those two keys, they are orthogonal. So this is again an ideal situation. In real systems, we generate keys based on pseudo-random number sequences, and they are then more or less almost orthogonal. Because in real systems, you cannot keep these nice perfect vectors. They say, okay, now I apply this inner product, the result is 0, they are orthogonal. So they are almost orthogonal, which is okay. Coming back to this example with the language, you will understand that okay, maybe the languages are not 100% orthogonal, but orthogonal enough to separate them. That was the basic idea there. Okay, and then I gave some more examples about how this can be a bit of visualized, this CDMA technology. And for us, it's enough to understand CDMA on this level. I also gave you an overview of the different technologies. You can always add polarization as well. And typically you will not find a single technology applied to a system. But for example, in the newest technologies, LTE, you have different frequencies. So we separate by frequencies, different operators, different channels, paired bands, unpaired bands. Plus, we have time slots. We also have different base stations. So, in Germany, for example, one of the operators has roughly 20,000 LTE base stations each year, 2,000 to 3,000 new base stations. That's quite a lot. And then we will see for the 3G technology UMTS, we also add CDMA, and depending on the level you're looking at, the multiplexing, you will find different combinations of these multiplexing plus algorithm, that means multiple access technologies. So that was the basic idea. Okay, so coming to the questions. We saw several effects, like, for example, this near-far effect. So mobile stations closer and further away with respect to the base stations. So first of all, how does this influence TDMA systems? If you are closer, if you are further away, think of TDMA systems. Do you have any idea what happens in TDMA systems? Okay, one answer, as long as the station can receive a signal and the signal arrives, at the right time. Very good. To hit the right time slot, it doesn't matter if the terminals are near or far. That's right. Synchronization, that's a big problem. So absolutely right. So as long as your signal is strong enough, it's fine. But we will see in the GSM systems, you have to keep up the synchronization, which is quite obvious. If you're further away, well, the signals need more time. So to be in sync with a certain pattern of time slots, you have to send either earlier or later in time. I will come back to this when we discuss GSM. So absolutely right. So that's a problem in TDMA systems. So what about CDMA systems? We don't have the time slots. So no problems with synchronization, but which problems might appear there? So exactly, it's the signals, the strong signal of the near terminal can actually influence the other signals. So this is exactly our cell breathing. That's the cell breathing effect. And the countermeasures, we already discussed them. So for TDMA, we will see we have to somehow keep up with the sending time. So we have to synchronize the devices. And in CDMA, what can we do there to avoid the problem? Forward error correction is one part of the answer. So indeed, if the error rate increases, we can do FEC, forward error correction. That is true. And what else we do have to do with the signals? Yes, it has to do with the distance to the receiver. So sending earlier, that's important for TDMA system. For CDMA systems, not the time, but the signal power. So you have to perform exactly. You have to perform very tight power control. And that's why those CDMA systems perform this power control really several hundreds up to 1,000 times per second, 1,500 times per second, because you need a very precise power control. So the idea is that all signals should arrive at the base transceiver stations with roughly the same signal strength. That's the basic idea. Okay, perfect. So we also looked at medium access control, and it's maybe for TDMA system it's quite clear, but also for space division, who's performing this? There are many different answers. What is the role of mobile stations, base stations, planning, etc.? Who's actually planning this multiple access schemes for space division? What does it mean, space division in a mobile and cellular network? Yeah, so the network provider is important because the network provider actually has to plan the network. And for space division, in the end, at a certain level of hierarchy, it's the position of the base transceiver station. So if you want to control medium access, you have to check, okay, where are crowded, densely populated, sparse populated regions, and this is where you have to apply your space division. That's one way. Then also, sure, the authorities, Bundesnetzagentur, whatever, and there are many more authorities regulating where you are allowed to place a base station. But also, now think of base stations. We looked also at a specific technology where you can do space division multiple access. Do you remember? Assuming a fixed base station and that can somehow follow mobile stations. Beamforming. Yep, exactly, beamforming. So SDMA today is also possible using this MIMO, multiple input, multiple output. That means several antennas. So in former times, there was a base station and okay, you had these sectorized antennas. They were not omnidirectional, but at least sectorized. But you could not follow a single user or single mobile station. Now with beamforming, you can follow this single station. Okay, so I guess I will not go into all the details of the next questions, but I mean, if you have questions, just please ask. But think of those terms like interference. Interference, what does it mean in space, in time, in frequency, and code? Okay, that's what I try to explain in this chapter. But what can we do, for example, in SDMA, TDMA, FDMA, and CDMA systems, so to avoid the interference? Keep minimum distance. Yes, for space, exactly, the centers are too close. So what does too close mean in time, in frequency, in code? And you see the concept is basically the same. So too close in space, it's quite obvious. Sending at the same time slot or sending overlapping. Yeah, overlapping time slots. Exactly. Guard spaces. Guard spaces, that's the keyword, exactly, guard spaces. And you need the guard spaces in time and in frequency, right? And what is the guard space in CDMA? It's not time, it's frequency. But there, what should the codes be? Orthogonal. More or less orthogonal. The more orthogonal, the better it is. Exactly. Okay. So, now you saw different medium access schemes, and now think of, okay, after looking at time, frequency, code division, you want to design a system that gives you really hard guarantees related to bandwidth or related to access delay. What would you choose? Feel free to pick whatever. So plan a whatever mobile phone network that has to give hard guarantees. Hard guarantees for the access. Or guarantees, so access delay or guaranteed bandwidth. Which would you pick? Different answers possible. So CDMA is one answer. FDMA, TDMA is another answer. Okay, let's go through those three. So for CDMA, to give hard guarantees, it is possible but difficult. That means you have to keep out other senders because you do not know how much noise they actually generate. So that's a problem. So access delay is fine because you can simply directly access the medium, no problem. But bandwidth might be a problem. Sure, you can control the access to a network, but the pure CDMA technology without any additional scheme, it's difficult because you might influence the others. So as always, there's no yes and no answers, so it always depends. For FDMA and TDMA, well, that's the simplest. The simplest at all is an FDMA scheme. Why? You assign a certain fixed frequency to the user, and only those users are allowed to use the channel. So that's something you use, for example, if you have to control something in an emergency. Then you could say, okay, there's a certain channel, and this channel is only for the firefighters. We will see how you can do this with TDMA as well later on, looking at the Tetra system. But for FDMA, you can say, okay, only the police is on this channel, or only whatever, a SWAT team uses this channel. And then there's no delay, and you have your guaranteed bandwidth as long as no one comes up with a jammer, etc. For TDMA, you can guarantee bandwidth because you can guarantee certain time slots in a repeated pattern. So every whatever 4 milliseconds you will have your 100 bits, and then you can calculate what your guaranteed data rate is. And access delay depends on the repetition pattern of your time slots. So TDMA schemes, it really depends on, is it demand driven or do you have this kind of fixed assignments? So we saw max schemes based on TDMA, where you might have an arbitrary delay because you have this random, this phase with collisions, where you do not know if there is a collision or not, and then you have the guaranteed phase, phase 1 and phase 2. We also saw fixed patterns in TDMA. That's what GSM uses, for example, demand-driven, not demand-driven. And we saw ALOA. ALOA under low load has no access delay. Great. Under high load, well, you have a problem. You cannot guarantee anything with ALOA. No hard guarantees. So ALOA, you cannot use it. So the point is, indeed, you can pick any of the technologies, but you have to be aware what do you have to do to guarantee something, to guarantee bandwidth, to guarantee certain delays. So that's the basic idea. So for many of the questions, there's not this right or wrong answer, but it's interesting to see what you think about the schemes and how you come up with a solution. Okay, guard spaces, we covered this already, orthogonal, so guard spaces between users use more or less orthogonal codes. And then there was something you could simply try on your own, that you say, okay, why not adding some random noise to the signal? And now again, simplified, we take the signal, we add some noise. So the result then is something like, okay, let's do this, -1, -1, 0, -1, +2, -1. So noise will obviously change these superimposed signal. So the signals from two senders, they superimpose in space. You get these transmitted mixed signals, then you add noise. That's just an example. It could be any values. It's noise. It's random noise. So then the receivers will receive this, and then you can apply the key, for example, AK. That was exactly always the idea. You apply this key, and then you calculate the inner product, and maybe if you remember the key, I also have to look it up. I cannot remember all the details. It was -1, -1, 1, 1. So that was the key. We apply this, then you will get 1 -1 +0 +1 +2 -1 equals something like 2. Okay, so so now this was the example for when the receiver tries to receive the bit from sender A. What happened? Well, you see, although we have noise, we can receive something. That's always true. It works. Exactly, it works. So there's still, the result is still greater than 0, and that was then our interpretation for, yeah, it was this bit was logical bit 1. It's just the interpretation. But now, if we add real life near-far problems, then indeed the signal of one of the senders could be that strong that if you add noise, you will not receive the original signal of the weaker sender anymore. So near-far plus noise, that's a problem. In our ideal world, near-far is not a problem because our vectors are really orthogonal. But in the real world, they are not 100% orthogonal. The symbols are not sent in a kind of a synchronized pattern. We have a lot of noise, all of this. And this really complicates, and that means you can easily construct situations where one sender drowns out the other and you will not receive the weaker one. In this simple world, you can add noise, whatever you like. You will always find out the original data, but that's not the real life. So that is, in real systems, more complicated. That should only give you the basic idea. So, countermeasures for near-far, we already covered this. Power control, that is the most important thing. And if you have this power control, so that you do not have this extreme strong sender B and the weak sender A, then the system works. You can play with this example, it simply works. Yes, as soon as those two vectors are not really orthogonal anymore, but almost orthogonal, so now all the mathematicians think, oh my god, but this is computer science, so almost orthogonal, then you will find examples where it does not work. So you will reconstruct a wrong bit. And this is exactly the situation where you then need something you already mentioned, forward error correction or checksums. So this is not a technology where you will get with 100% the correct bits out of the system. But this is also true for TDMA and FDMA systems. So in wireless transmissions, keep in mind the bit error rate is, well, 10 to minus 2, 10 to minus 3. That means 1 out of 100, 1 out of 1,000 bits are flipped. So you always need some coding technology on top of that. And this, by the way, is the reason why we have the delays in transmitting data using wireless systems. We have a certain algorithmic delay because we have to calculate checksums, forward error correction and all this. And this takes some time, not the calculation, but you have to actually calculate the forward error correction using a larger window of bits. So you have to collect some bits, calculate the FEC, and that introduces a delay. That's the basic problem of all wireless technologies. Okay, so that were some of the basic questions for CDMA technology, and this also wraps up the lower layer, so to speak, layers 1 and 2, so medium access in a very general way, and also what happens to signals. And this is now the point where I have to ask, are there any, let's say, fundamental questions or questions related to medium access, to all this signal stuff, to all these things that are closer to electrical engineering? Okay, currently I don't see any questions. If you come up with questions, just send me an email. Some of you already did. Please feel free, and then I will answer them. And I can also come back to these questions then the next time.